Okay, very good. So we can start. And I would like to start it at the point in which we stopped yesterday. Namely, yesterday we were discussing BCFW recursion. And the last thing I wrote, or one of the last thing I wrote, was a formula, a recursive formula for the physical amplitude, which recall that this is evaluated in terms of a complex parameter. And this was expressed as the up to an overall normalization, the product of two lower point amplitudes, but shifted at a specific value of these complex parameters divided by pi squared. And then this was a contribution coming from poles. I should mention or recall the formula for Zi. And of course, to explain this picture, we need to have in mind some assessment about the different channels of factorization for an amplitude, so that we have a part on the left and a part on the right of the amplitude, and each pole on the complex plane corresponds to one intermediate propagator going on shell. And this I is the set of external lines which corresponds to the amplitude on the left, with the understanding that if you are dealing with color order amplitudes, you want to preserve ordering. Otherwise, more factorization channels are possible. So as I introduced this, I mentioned the fact that, of course, if you want to apply the residue theorem, you need to consider also the pole at infinity, or the behavior, if you wish, of your amplitude for a large value of the complex parameter. And this is in general what, if something goes wrong in this method, is related to typically forgetting contributions from infinity. So the fundamental question here is how can we assess whether a particular shift works or doesn't work? And in this respect, I would like to give a simplified argument coming from one paper, which you can read if you want to have a full treatment of this issue. And this is a paper by Akanyamada and Kaplan, who studied behavior at infinity for a variety of shifts in different theories. So this is a nice read, and this is a fairly pedagogical paper in which you can find more details. I think my role here also, not just as lecturing, but perhaps suggesting a couple of references which you may find helpful if you want to study this subject further. So here I want to give a sketch of the proof, with referring you to the paper for all the details. Just for me, it's important to illustrate how would an assessment of the behavior at infinity look like. So in practice, what we're having is that there are two hard momenta. Recall that I'm not going to write again the properties of the shift, which we have considered. You have to look at the notes from yesterday, but we decided to shift, in this particular example, the leg number 1 and leg number n. So for large value of the complex parameter, we end up having a situation in which each of these is equal to complex parameter times q is the shifted momenta, plus corrections, terms which don't grow in the complex parameters. So the other observation is that the other momenta are soft. And the argument from this paper relies on using a variant of the background field method. This relies in splitting our vectors, essentially in a soft part, and then the hard fluctuations. And of course, we will consider an amplitude which has exactly two hard particles, the one in position 1 and the one in position n. So there is some, after doing some work in rewriting the Lagrangian after gauge fixing, in this particular case, becomes takes on the following form. So if we use the trace formalism in that we are dressing our gluons with a representation matrix. Again, these are the hard fluctuation. We have a kinetic term of this form. Notice that there is no anti-symmetrization here. These indices are contracted exactly as it is displayed. And then there is a trace here of the anti-commutator of two hard fields, the F mu nu. And here this is the soft F mu nu, so to speak. It should also be remarked that the soft fields are also hiding inside the covariant derivative here. So this covariant derivative is with respect to the background of the soft fields, whereas this is the hard fluctuation, same thing. This is the background. How do you get a kinetic term of this form? You need to put in a gauge fixing term. Gauge fixing term, which would be a little bit different from the usual one in the sense that it would be something of this form. There would be the trace over, this is the equivalent of the Lorentz gauge condition, but in here again, soft field is in the covariant derivative. You do this, and after gauge fixing, you get a Lagrangian of this form. Okay. So the next step is actually noticing that in this particular Lagrangians, there is a situation in which the indices, the space-time indices carried by the field, the hard field A, play a different role with respect to the space-time indices of the derivatives. In other words, I can rewrite the Lagrangian, and this is a complete trivial rewriting, in a way that makes it clear that some of the space-time indices here are treated in a sense separately from the one carried by the derivatives. So this is a situation that corresponds to having this is a situation that corresponds to our very simplified setup. Again, the job of this Lagrangian is to compute amplitudes in this particular limit. So this is why we can have a series of simplifications and we don't have to resort to the full calculation of the amplitude. Yes?
Could you repeat why you changed the name of the indices?
Well, you can see here, this is rather trivial. So you can see here that the space-time indices of the derivatives always contract with each other. So I just changed the name. Of course, it's a dummy indices. I can always change the name, but I want to treat in writing down the Feynman rules and calculating the amplitudes, these indices in a different way. Simply on the account of the fact that I know that this index will always contract with each other and then or contract with the one in the background field. Okay. But this is a very good question. This is, in a sense, the heart of the argument. So the question here, the heart of the argument is really that and the implication in terms of what kind of Feynman rules we get from this simplified Lagrangian. So generically, the kind of graph I'm having, and here I am drawing with a continuous line. our hard particles, gluons, and then there's going to be, of course, insertions here. So what kind of vertices can we have? The first thing which is important to remark is that the propagator in this particular case goes like 1 over z, not 1 over z bar, z squared, sorry. Why is that? Because even though the momenta, right, I mean, the momenta here carry a factor of the complex parameter, q is a null momentum. So you end up having a 1 over z out of the propagators. And then we are considering this vertex, right? So this vertex has, there's two of such vertices, one coming from the covariant derivatives and one coming from that. So perhaps we should label them in a different way, but the way this vertex behaves, it carries a factor of eta ab following these indices, and then there is a constant for a complex parameter plus another constant plus a term that is of order 1. Okay, so the final form for the amplitude, and again, we care about the leading z behavior, is going to be something of this form. Of course, I'm going to have two indices just two indices corresponding to the polarizations of the hard particles. And then we're going to have a constant here, a term linear in z with terms here which are of order 1. How do you get the term which grows like z? Well, you need to have one of these vertices. All the vertices needs to be of this kind, right? Because then you would have one more vertex than the number of propagators, and you would end up having a term which grow linearly in z. So this is some term which we want to kill in the final amplitude, so to speak. But the important thing is that this is proportional to eta. Then there will be a linear term proportional to a tensor here, which is taken to be anti-symmetric, because this is coming from the FAB for the background field, which is indeed anti-symmetric. And then there will be terms that are of this form. And these are the good terms. So I'm not going to say anything about B because I like the fact that it goes down as 1 over z. Okay, very good. So questions about this form of the amplitude? This is one of the steps that I think, yes? This one? Okay, very good. So where can a factor proportional to z come from? This needs to come from the momentum, or that is from one of the derivatives in here. This is not the only vertex also. We can say that another vertex will come from here, and this vertex, let's perhaps give it a different name. So I indicate with a ball, and maybe this comes like that. This would be proportional to FAB. But here there is no derivative, right? So this does not have any term which grows linearly with z. So there's going to be linear z dependence from this. And then there's going to be, of course, terms in which there is a constant. There is no z dependent, but they come still with an eta. And then there will be a term in which the antisymmetric tensor appears. Okay. So we consider all our amplitudes, and we are concerned only about the terms which either grow linearly with a complex parameter or are of order 1, and then all the rest would result in a good behavior. And we identify the most pathological term as the one coming from a series of indices of vertices of this kind. The key property here is that whenever you find something linear, z is multiplied by this matrix. And then there's also potentially problematic term, which comes from just a sufficient number. I mean, just the insertion of one of these vertices. because keep in mind that the propagators take down the power. In that particular case, this would be proportional. I mean, it would not exactly be disverted, but this will be antisymmetric. So we are using the property. The properties which we will use are proportionality to eta and antisymmetry of this, together with the fact that, for example, this cannot grow linearly. This needs to be a constant, and this can grow at most linearly because of that. Okay. Next, this amplitude needs to be gauge invariance. So gauge invariance of the amplitude takes on a form. So let's see. We have so we are replacing the epsilon gauge invariance for leg 1 for the asymptotic state 1 takes on the following form. Here we have still the polarization for the leg n, and this needs to be equal to 0. What does this mean? Well, this means that P1 minus, so this is the same as P1 plus ZQ A is Q1 is the corresponding shift, as I said before. This is the same rewriting. This is the shifted momentum, and this implies in particular that if you have Q1 A, MAB epsilon Bn is equal to -1 over the complex parameter P1. P1A, yeah, of course, the amplitude MAB. So I can use this relation to reduce the power in the complex variable. Okay. So the next step here is to take into, so carefully writing down the various polarizations in this particular element. And of course, in this particular limit, let me see. In this particular limit, we just need to care about the leading and in some cases subleading behavior for large complex parameter. So this is a small exercise in spinorilicity, and what I would like to study is not just whether this shift works or not, but also for what polarizations of the external lines does this work. And the final result is that there needs to be, for the shift to have a large Z behavior which is acceptable, that needs to be with certain value of the polarization of the shifted lines. So this is important to keep in mind. So for example, in the shift I gave before, we are having that the positive polarization, the polarization, the unshifted polarization, well, we write it first here. Factor square root of 2 is not important. And then under the complex deformation, this behaves like same term, of course. And then there is plus a complex parameter n. So we see that this shift is actually proportional to the n momentum. So there is still the bracket in the denominator, but we observe that actually this is proportional, the shifted parameter, to the nth momentum. Okay. How about for the minus polarization? So the minus polarization stays unshifted because the shift, as you recall from yesterday, affects the angle bracket of n and the square bracket of 1. which don't appear. So this goes into itself. There's no shift. Same thing for the positive polarization for leg n, for the last leg. This is also unshifted, going into itself. And the final one, the negative polarization for n, it's picking up a term which is linear in the complex parameter, and perhaps unsurprisingly, you can see the systematics of this, that this numerator is proportional to the momentum of the other shifted leg, namely P1, with the opposite sign. Okay, very good, yes. Sure.
Was there an implicit choice of reference from the beginning? You chose the reference for the polarization to be beta 1.
Yes.
Why is it picking up a factor of x if we're shifting with q?
If we're shifting with q? Yes. So in this particular case, very good. So the shift momentum here for q is built essentially by the 1 squared and then the n angle bracket. So in this particular case, as you said, there's been a choice for the reference momenta into this. We are using a reference momenta for leg 1, which is leg n, and vice versa, which relates the q, which you see in the expressions for the polarizations, with the q, which you see in the shift. This is not something which needs to happen, but in a general BCFW shift, but this is something that can be helpful in this calculation. So that is a very good point. Okay, anything else about this? Okay, so what I need to do next in this is just inspect different shifts. And I would like to consider in particular 2 shifts which will end up being good shifts. And then you get an idea on how this is done, and you can consider all by yourself all the other shifts if you like. So I want to consider the shift minus plus. And keep in mind that in the way in which I have implemented my recursion, the order of this plus and minus. So leg number 1 is a leg in which the shift involves only the square spinner, right? So having a minus polarization here is very much related to that. So what is this? This is, of course, just as a trivial rewriting of the formulas which we have so far. By definition, the amplitude which we have here addressed with this. And then we look at what is this proportional to. So we are having epsilon 1 minus, and we see that this is that this is proportional to, so epsilon 1 minus is proportional to the shifted one, and this would be, this is not true, that's Q conjugate. So this would be proportional to 1 n in this particular case, and also keep in mind that Q defined in this way, as you can see by using complex conjugation rules, is a complex spinner. So we call Q star the conjugate, which would be here n. And here we will put the 1. Okay, very good. So with this, we see that this is proportional also to Q. Where proportional, I mean that the numerator over there, of course, there's also division by, in that particular case, a square bracket. So this is just to say that this is actually proportional up to division by a square bracket to this plus b for the n leg. Okay, and this is, of course, something that allows me to use the relation over there. And here I should be Q1 is equal to Q, notationally to be consistent. Okay, very good. So by using that, that relation, I can actually rewrite this as minus 1 over the complex parameter. And then we have P1A, MAB, epsilon B plus N. We are almost done. Sensitive would say this is something that can be made problematic only by the term growing as the complex parameter in M. So in that particular case, this will become proportional to 1 over the complex parameter. We have the P1, and here we look at the term which is proportional to the eta matrix, and then we have the antisymmetric term. The antisymmetric term would not be problematic. So we see right away that this is proportional to 1 over the complex parameter. This is the leading behavior, and here I have used simply the fact that P1, by construction, the scalar product between P1 and Q is equal to 0 with this choice. So this is a good shift. In other words, it goes off as 1 over the complex parameter for large value of the complex parameter. Another shift, which is a good shift, is the one with 2 minus polarizations. This would be proportional by the same argument before, as minus 1 over the complex parameter P1, and now we have again the same term coming from the general expression for the amplitude expanded. But now, instead of having something which is proportional to Q, we have a potentially problematic, one more potentially problematic term, because we see that the minus polarization as a term like this. So the minus polarization, the epsilon minus, as there a term proportional to Q, the complex conjugate, so Q star B, minus complex parameter P1, that term over there, B. So here we actually get that this is equal, again, to 1 over the complex parameter P1A, AB, Q star B, Q complex B. And this is the consequence of a series of cancellations. So, of course, you have that P1 dotted into Q complex conjugate is going to be equal to 0. This is by construction. Or if you like, because you can see that one piece of the Q star is made by the one angle spinor. You also using the fact that P1 is null. So because you're going to have a term here in which P1 gets squared. And also, finally, you're going to have a term, which is still a potentially problematic term, right, coming from a P1 matrix here and a P1 in here, because this would we would go to infinity as a constant, but you use the fact that AAB is antisymmetric. Very good. So of the 4 terms which you can write down, this is the one which is left, which is a perfectly good term because it's a 1 over complex parameter. So in other words, we have shown that the shifts that we have discussed, namely minus, plus, we would call it, and minus, minus, are good shifts. Okay. Good shift meaning that the pole at infinity is absent. So you just get a recursive contribution which comes from the poles in which intermediate channels go on shell. Another fact which I would like to note is that not all shifts are good shifts, obviously. So if you consider this shift and you repeat the same calculation, you would find that this is not a good shift. And notice here that there is a correlation between the kind of shift, namely leg 1 was shifted here by the square spinner was shifted, and the polarization, right? You have a plus polarization on leg 1. So this is the example of a shift which we should not use. Okay, very good. Questions about this? Yes.
A couple of questions.
Mm-hmm.
I still don't get completely the difference between good and bad.
Okay.
So, in that case, for instance,
Mm-hmm.
so you do this shift, you find that your overall amplitude contains two types of contribution.
Mm-hmm.
One where intermediate channels go shell, but there is on top of that another contribution coming from the pole at infinity.
Yes.
What's intrinsically wrong with that? The amplitude contains two types of information.
Yeah, absolutely. And so, okay, so I guess the question here is what is bad about a bad shift? There is some information which you don't obtain immediately from lower point amplitudes. So the question here becomes how can we get some control on the pole at infinity? And there are some ways of doing that. I think it is preferable not to have the pole at infinity if you can. So if I have a choice, like in Yang-Mills, my takeaway message would be use the good shifts. But the meaning of the pole at infinity is that there is some information which is missing, and that information is physically relevant. And if you find a way of using it, this is a perfectly good result. So yeah.
About theory being effective and therefore that there could be extra higher
Yes.
reference that
Yes.
hidden there and you want to be agnostic about that.
Yes, absolutely, absolutely. So ultimately the root, so if you have an effective theory, right, so that is an effective theory in which new information is provided at each multiplicity, then you will have that this information shows up at the pole at infinity. That is absolutely true, and it depends really. I mean, the choice for you is how you want to convey this information. I mean, the typical trivial example is phi to the 4 theory, right? What is the behavior of the 4-point amplitude at a large value of the complex parameter? Well, it goes as a constant because there's just one diagram, which is a contact diagram, right? So what does this mean? There's something wrong with the theory, or that simply you have that physical information which you provide the 4 points? Obviously, it's the latter. If you start putting in a new vertex, no dependence on the momenta, or with perhaps some dependence on the momenta, then you would necessarily, unless the vertex is non-local for some reason, you would necessarily have an information which comes in at infinity because you don't have a large Z behavior. So part of this is also how do you want to specify your theory. However, for renormalizable theories, there are some results by Elvang and Kermeyer that say that they identify a family of shifts which actually works for these theories. And this makes a lot of sense because you expect a renormalizable theory, obviously, to have all the information in lower point amplitudes, and then higher point amplitude just follow naturally. But this is not a shift which falls into the most elementary BCFW form. Namely, these are all leg shifts. And this is a little bit more complicated, I would say.
So this applies to 1 factor 4 as well, legal
that would be, yes, in that particular case, however, you would have a situation where lower point amplitude, so you cannot start from 3 points and bootstrap the 4 point. You need to start from 4 points. But that's a rather obvious thing to say. Okay, so just a couple of comments here. In many introductions, and even if you go read Evan and Wang, this evaluation of the pole at infinity is kind of done in a very quick way. I wanted to give you a taste of how this study of the pole at infinity would look like. And now, I think that in the 10 minutes which we have left, I would like to start actually discussing probably the most famous application of these techniques, namely looking at the expression for MHV amplitudes at endpoints and being able to prove that recursively. Stop me if you have other questions before I cancel the blackboards. Okay, very good. So what I want to do is to show the Park-Taylor, that's going to be the name, formula for MHV amplitudes at endpoints. So in this particular case, we are going to have an amplitude in which all polarizations are plus, except leg 1 and 2. And in this particular case, we are having the formula which we want to prove is a generalization of what we had before. So here we still have 1, 2 to the 4th in the numerator, and we have the sequence of angle brackets which corresponds to the ordering which we have here. And the first check for this amplitude is, does it make sense in terms of helicity scaling? You can verify this right away, that leg 1 and 2 have helicity weight -1, and the other ones have helicity weight +1, as it should be. So the question is, can we prove this by induction? Or if you prefer, by BCFW recursion. So we use a shift, which is a minus plus shift, so one of the good shifts which we identified before. And then we write the n amplitude as we get essentially two terms, two kinds of poles in here. So this is an ordered amplitude, okay? So we divide into two parts the amplitude here, and we have to have a contribution to a pole, we need to have the shifted legs, which are 1 and n. They will need to be on opposite sides, of course, of this channel. Given the cyclic ordering and the fact that n and 1 are ordered in this way, we are going to have the legs. Oops, I need a little bit more space here, sorry. We're going to have the legs here, and then there's legs 2 as a minus. And then there's going to be a certain number of legs on this side. We stop at legs I, right? And then we start from legs I plus 1. Part of this is just labeling the legs. And we go all the way to legs n. And then why there are two terms into this? Because since I am considering on shell states, I need to consider two opposite situations. The one in which you have positively polarized gluon here and a negatively polarized one, or the other way around. Okay, so here we have the same situation, but the opposite polarization, minus plus, and let me just, we start from 1, I put a hat on everything which has been shifted. Here again we go I. There's a minus and a plus. Here this is I plus 1, plus polarization. And then we go all the way to 1. And the summation here is over possible insertions for I. So at which point I stop from the amplitude on the left and I start putting I plus 1 on the amplitude on the right. Okay. The ordering is, of course, kept fixed because we are dealing with color-ordered amplitudes. Now, what is important to point out in this case is that most of these amplitudes are equal to 0. Why is that? This has to do mostly with properties of the MHV bar amplitude. So in general, if we are having amplitudes, so in this particular case, we are having that we need, in this particular case, we have an amplitude which is an all plus amplitude, right, regardless of the value of I. So this is always going to be equal to 0. In this particular case, instead, we are having a situation in which we can have an MHV amplitude at lower point on this side, and then there's an amplitude here with 1 minus. You would say for generic multiplicity, this also vanishes, but there is an exception. And the exception comes at 3 points. So at 3 points, we have an anti-MHV, we call it amplitude, in which you have n and then minus 1 with positive polarization, and then pi comes in with a negative polarization. So in other words, and this is really where you start seeing the simplicity of this, we express in the following form, and then I give you a break before I solve it, this recursive relation. So let me make a little bit more space. So there is 1 shifted minus polarization, 2 unshifted, still minus polarization. Here we have n minus 2 plus polarization. Try to be very explicit about this. We call this pi, and we put a plus polarization also in this particular case with a hat, because it's also shifted. And then there is a pi squared in the formula, and we have an A3. In this particular case, this is n minus 1, n minus A3, and in this particular case, we have minus pi hatted. This is a minus polarization, n minus 1 plus polarization, n plus polarization, and this is hatted because it's shifted. So one can say that this is an MHV amplitude, and one can say that this is an MHV bar, or anti-MHV amplitude. And for this, we have expressions which we will use after the break to finally prove or argue for the endpoint result. So any questions before we take a 15 minutes? Yes?
Why didn't you consider the 1 and n are the same as amplitude?
This is a very good question. And the answer is because you would not get a pole in that way. Right? Because if something else, if some other polarization, so you're referring to a polarization, to a configuration, I'm sorry, like this, right? 1, n. These are shifted. Then by momentum conservation, and property of the shift, remember when I give you the basic properties of the shift, it needs to conserve momentum. Then this thing can, of course, go on shell, but there's no dependence on the complex parameter. So when you are studying the behavior on the complex plane, not for all momenta, but for this particular complex parameter you have identified, you don't get a polylinear. Okay, because this pi is unshifted. Consequence of the choice of Qs I have made, and ultimately the property demanded in terms of momentum being conserved, still after the shift. Does this make sense? Very good. But this is one of the key points. And of course, this simplifies a lot the calculation, because then I have to consider all diagrams in which one and then on opposite sides. Okay. Very good. So please try to be back in 10 minutes, 12 minutes, so that we can start on the hour sharp. Okay, very good. So we can start again. Fantastic, on the hour. What I would like to do is to conclude this calculation. So the next step, again, just to give a quick reminder, we are using BCFW recursion, and we have argued, based on vanishing of some amplitudes in which you just have one minus sign and all pluses, or all pluses. We have argued that there is only one, in these summations, there is only one surviving term, namely the one in this class in which we are having an MHV amplitude at lower point on the left, and on the right, we're having a particular situation in which this is a 3-point anti-MHV amplitude. All the other ones will vanish. This is the only exception to the rule that when you have one negative helicity and all the rest positive helicity, the amplitude should be equal to 0. Okay, and thankfully we already know the forms of these amplitudes, so this can be done as follows. And of course, this being a recursive proof, I will assume that expression for the lower point at the n-1 amplitude. I will, of course, use the result at 3 points, which is already known. And here I attempt being careful, and I will hat everything which is shifted, which is easier, makes it easier for you to understand where the complex variable is hiding. And the complex variable, of course, we are at the pole, so it takes the non-zero value, which we wrote before. So this is the n-1 amplitude, so there's n-2 pi, and then there's going to be a pi here and 1. Okay, there is a 1 over pi squared piece. And then here we have n-1 unshifted, n shifted to the cube, and a bunch of square brackets. So there is pi, here n-1. Here the minus sign indicates, and the fact that, of course, we identify this is the outgoing momentum from the first graph, but then since we are having conventions in which all particles are outgoing, this will be outgoing with a minus sign on the second amplitude. And then there is an n shifted minus pi here. And this is all that there is. Okay, very good. So now we need to use some identities to rewrite some of these terms. In particular, we see that here we have a potentially very long string of terms which are already in the result we are trying to find. So the basic strategy for us, same from the numerator here, the basic strategy would be to combine these two objects with these two objects, throw in this, and simplify things in a way that reduces the amplitude of we want. So I will start by noting a few things. So in case I need to define what happens in case, or rather than define, to adopt convention in the case in which we're having a negative moment as one of the brackets. So what does it mean that you have a negative moment in one of the brackets? Well, you want to have that there's a minus sign in the momentum coming in spinor Aristide notation. So you have to choose conventions, actually, according to which either the lambda or the lambda tilde spinor will pick up a minus sign, but not the other. And we will choose conventions so that where the star can be anything of the other momenta, the minus sign is carried by the square bracket. Of course, you can see the minus sign coming in pairs, so this choice doesn't make any consequence. I could have had the other one. The other thing I want to say is that pi squared, we are using here momentum conservation. We are using here momentum conservation for the unshifted momenta, because remember, this is not shifted. Otherwise, it would be a 1 over 0 singularity. And so this is by momentum conservation, which is very simple at 3 points here. We write this as Pn dot into Pn minus 1, which in turn we write in terms of angle and square brackets. Unshifted, which is equal to n minus 1, keeping this unshifted. But then, since the shift for n only involves the angle spinor, it is trivially equal to the 1 for the shift, with the shift. Of course, here, I keep this unshifted, which is a good thing. Okay, so this is what happened that, and then I would want to combine the two terms over there from the angle brackets with the one of the square brackets and try to use momentum conservation. I'll show you what happens in one case. So we have the angle bracket between pi and 1. And we put this together with the square bracket with pi and n minus 1. You can also do it with the other one if you like. So this is equal to minus, just reversing the order of one of the brackets. Here we have pi. If I really want to be careful, I indicate it's contracted with gamma matrix. And this is the other spinor. Now we use momentum conservation. So pi is equal to, with a plus sign, Pn plus Pn minus 1. Using, if you prefer, the Dirac equation, the n minus 1 gives a 0 contribution, and then only the n here, and n minus 1. Gives a contribution there. Okay, so since this is, it should be said, since this is hatted, then we need to keep the hat in there. And the one, again, the one is shifted only the square. If you remember the shift, there's details on the shift that you have to flip a couple of pages of notes back. I'm not putting in, I don't have currently on the blackboard, but shifted and then shifted. For one, the angle spinor is the same. Okay, very good. So this is one of the results. You do the same manipulation on the other one, n minus 2, pi shifted. Here we have n shifted, pi shifted. And by following the same steps and manipulations is n minus 2, n minus 1. So that's momentum conservation is still used, but in this particular case, even though pi is equal to pn plus pn minus 1. In this particular case, the Dirac equation you're using is the one for leg n, and so the n minus 1 is left in there. Okay, so here are the same steps. Okay, and also note that 1, 2 is equal, which is equal to 1, 2. Again, because of property of the shift. Very good. So using all that, we can simplify our amplitude. An, so there's an overall factor of I. There's the part of the amplitude I mentioned before that goes along for the ride, that doesn't involve the pi part. And this is all the way to, say, n minus 3 and minus 2. And then there are the new terms. So we write everything that is over there. So pi, I start by writing the pi squared, as I've done that above, and minus 1, and minus 1, n shifted. Okay, then I start writing the two combinations I brought over there. There is here also 1 shifted and shifted, which I have over there. 1 is also the same as unshifted, and shifted and minus 1. That's the third line over there. And then I continue by finishing with n minus 1 angle brackets, and then there is, I have to put it here, n minus 1 n. Okay, and at the numerator I still have this n minus 1 n shifted at the third power. Okay, very good. So there's a number of simplifications which happen here. So this simplifies with the numerator. Same in here. And same in here up to a sign. This is already gone. So what we are left here is I, the desired numerator, and then we have 2, 3, cyclic ordering up to n minus 2, and then we have the n minus 2, n minus 1. Did I write the n minus 2, n minus 1? I'm gonna. I think, yes, the last one. Yeah. Where did I got this from? Okay. Thank you. Very good. N minus 2, n minus 1. So let's see, all the rest is correct, presumably or hopefully. So here we have, very good. So here there is n minus 2, n minus 1. There is the n minus 1, n. And then there is the n1. Okay. And the overall result is the desired one. In the last step, we've used that n hat 1 is equal to n1. So the spinor n is shifted. This is shifted, but the shift is proportional to 1, so this vanishes. And this is all that we needed. Very good. Okay, so this is proves recursively the formula for MHV amplitudes at endpoints. One obvious thing which should be remarked is that at points starting from 5 points and onwards, well, sorry, starting from 6 points and onwards, you also can have next to MHV amplitudes, which are, in general, have a more evenly matched number of polarization, and they are more complicated. So in other words, this strikingly simple formula happens only for a particular subsectors of amplitudes, which I have identified by helicity weight. So namely the fact that I can divide amplitudes in 4 dimensions according to the number of positives and negative helicity gluons. It allows me to pinpoint this particularly simple family of amplitudes. That formula which you have seen, the Park-Taylor formula, has been, in a sense, a precursor for many modern amplitude methods, in the sense that in the 80s it was remarked, it was identified that after what at the time was a Feynman rule calculation, you would end up to have a very simple result, despite complexity of the calculation itself. And this has been one of the driving observations for the field. The fact that with the right variables, you have very simple expression for amplitudes at 10 points. Another thing I wanted to remark, but it is beyond the scope of these lectures, is that you should, I hope, you should appreciate how there is a lot of freedom in identifying these shifts. And in particular, you should not restrict yourself if you're working on this topic on having just shifts involving 2 legs. These are the simplest one, allow me to sort of illustrate the general features of these methods, but for example, some authors resort to all leg shifts. If you want to read a little bit more about all leg shifts, I would recommend Clifford Chang's TASI lectures on amplitudes, where you have a very pedagogical introduction to also more general shifts. Okay. Questions about this? Because otherwise, in the last half an hour, I would like to start sort of a new chapter or a new topic. Namely, I would like to discuss supersymmetry. So, supersymmetry has been conspicuously absent until now, but I think many of you have this idea, I've heard, I mean, I've been exposed to this notion that amplitudes in supersymmetric theories will be the simplest ones. And indeed, part of the selling points for the amplitude technology has been an easy or straightforward way of incorporating or maybe representing supersymmetry on these objects, right? Because typically supersymmetry is represented with the help of a superspace which exists off shell. And I think virtually all of you have been exposed one way or the other to supersymmetry in this language. But, or not. But in case of amplitudes, there is actually a slightly different description which occurs on shell. Amplitudes being intrinsically on-shell objects, then we need to rephrase this with on-shell language. So, let's say. So the basic idea of a superamplitude, and I really try to provide here an elementary introduction, is that we want to complement, instead of having an amplitude which in general is going to be a function of kinematical data, polarizations and momenta, for example, for external particles, we want to complement this or turn this into an object which incorporates extra parameters. And this will be, we call this etas, and this will be Grassmann variables. So in a sense, the notion of a superamplitude would be a generalization of amplitude which accounts for extra kinematical data that characterizes no longer the asymptotic state, but rather the supermultiplet in which the asymptotic state lives. And in particular, we will focus here on the simplest example from an amplitude perspective, that is n equal to 4 superior mills. So as much as part of the formulation of amplitudes involves the definition of the asymptotic states, so before we are discussing superamplitudes as functions of these parameters, I would like to ask the simpler question. It is, how can we organize the state of n equal to 4 superior mills in terms of superfields? This is, since we are discussing states, what we will discuss is a non-shell superspace. Or on-shell superfield, if you like. Where we will have now that there is, the superfield is a function of some Grassmann variables, and we will be concrete about this and attach an extra index to these variables. This index being an SU4 R symmetry index. And then we can organize the states of the n equal to 4 supermultiplet in an expansion in these Grassmann parameters. One of the questions I had when I was preparing these notes, I mean, I had this question in mind, I didn't get obviously an answer, is how much are you familiar with Grassmann parameters of superspace? Do I need to say anything about Grassmann variables, or is it something that you consider you're shaking your head? Okay, please let me know if there is something that sounds a little bit strange. So one of the basic properties, of course, of having these Grassmann variables, which are anti-commuting variable, meaning this, obviously, is that the expansion is truncated here. So you go also to a certain number. So if you have just a single Grassmann variable, well, actually any function, an analytic function is very simple there. You have a constant and you have a term linear in the variable, and that's it. Here we have 4 variables, so we expand this up to terms with 4 variables. And then the full expansion will be something on this form. So you start having a fermion with one of these indices, and then you get a term which is a scalar. And then there is a multiplicity factor, which part of this is conventional, but then the reason of the convention is to account for all different permutations of these indices. Here we're going to have a fermion with the minus polarization, and then we weight 1 and 1 and 2. Sorry, eta 1, eta 2, eta 3, eta 4. We're going to have the minus polarization for the gluon. Okay, so something that you see in this presentation of the amplitude is the obvious fact that, well, this is very simple. And the simplicity was obtained at the price of breaking Lorentz invariance, because we are having that there's a gluon here, there's a gluon here, and as far as we're labeling states, right? States are labeled by their arylicity, I can do this, but if you want to have a covariant description of a superfield like this, it would break Lorentz invariance, it would be extremely problematic. Same thing for breaking different polarizations for the fermions, and of course, counting the states here, you get the right number of scalars, for example. And the right assignment of the R symmetry indices. Okay, so having a presentation of this form, we also note that, yeah,
With an epsilon, for index,
yes,
define the lambda minus with the lower
yes,
index.
yes.
Would be more symmetric.
Yeah, yes, we could do this. Um,
It doesn't change the substance.
no, it doesn't change the substance, but some authors, some people would prefer probably to do it in that way. Okay, very good. I mean, of course, all the manipulation of SU4 applies. So SU4 has an invariant tensor with 4 antisymmetric indices, and I can always use it to simplify. Yes, that's a question?
Yes.
Yeah.
So this object A plus, lambda A plus, and so on are all ordinary fields depending on the ordinance of the.
Okay, so these are, well, I mean, these are asymptotic states. So I don't interpret that as fields, it's rather asymptotic states, or if you prefer, you can see all of this as being, say, creation annihilation operators, and then you stick that into an amplitude. Very good. And then, of course, these are norm. I mean, these are bosonic object. Well, these are bosonic or fermionic object, because in this particular case, this is a fermionic object. And then the etas are Grassmann variables. And one last thing I want to use is operationally, you extract components here through the help of differential operators. And the operators are defined, I mean, if you want to extract a component A plus, of course, that's the identity operator. Lambda plus with an index A becomes a differential operator in the Grassmann variables. You are having phi AB, which becomes the double differentiation with respect to the Grassmann variables, and so on and so forth. The normalization which you see here in the fields is so that unit normalization is used for these differential operators. Okay. Very good. Questions about this? So yes, this is true. You set the other parameters to the parameters to 0 when after you're acting with this. So that would effectively kill the other components. Very good. Anything else? There's one last ingredient I want to put on the blackboard before we can start discussing this, which is actually a definition of supercharges. Of supercharges. Or rather one particle supercharges. So if we have an individual particle, you can define a supercharge as we're having here the angle spinor, and then this acts by multiplication with the Grassmann parameter eta. A second way of defining this or a second supercharge here can be defined in terms of v square spinor. And in this particular case, we have, hang on, we are having this, for consistency, it's a high index, so this is differentiation with respect to the Grassmann variable. Okay, very good. So with this definition of supercharges, we recover what I bet you've already seen in terms of supersymmetry algebra. So namely, we are having that we're taking the anti-commutator of Q, which I have done there with a lower index. So I better stay consistent, and then there is the Q dagger here with the dotted index and the high B index. This is equal to, you just use, the definition, I would say. The expression, the combination of the two spinors, the lambda and the lambda tilde spinors, with which corresponds to momentum. And again, this combination is, just to write it in a more familiar place, in a more familiar form, the contraction of the momentum with the sigma matrix, and then there is, this is exactly the usual form of the supersymmetry algebra with a slight difference in the usual normalization. I mean, if you go on Wessenberger, for example, there's a factor of 2 here, which is just a different normalization. For an amplitude, we define the supercharges, say A alpha, as the sum of these objects associated to each individual asymptotic states. Same thing for this. Okay. This being the difference between the one particle states and the collection of asymptotic states which characterizes the amplitude. Okay, questions about this setup? Very good. So then, that's a question, yes?
How should one think of the supercharges in this? Are they operating? What are they?
Okay, so this is a very good question because I have not yet told you what they are acting on. Right, so these are, I want to have an object, which is the super amplitude, and the super amplitude will be, well, this, right? It would be a function of kinematical data, including the etas. And then these objects are designed by acting on it, and the fact that it's a super amplitude, it's invariant under certain supersymmetry, will translate itself in the fact that they annihilate it, that they kill it. Okay, so actually that was one of the next things I wanted to write. So the super amplitude here. Let me try to have a notation in which I can differentiate between amplitude and super amplitudes. So the super amplitude is a function of, at endpoint, of my super on-shell superfields, or the data on the on-shell superfields here. So namely, this will be a function of the superfield corresponding to n particles. And this is, in other words, corresponding to my the set of kinematical data for each external lines, which now include the Grassmann parameters. And then we can extract individual amplitude. by acting with the differential operators. Associated to each individual state. So for example, the amplitude. Say that we want, since now the MHV amplitude looms large in our imagination, let's say that we want to extract this. What would this be? This would be the action of the differential operators corresponding to leg 1 and leg 2. So this is corresponding to leg 1, the differential operators with respect to all 4 Grassmann variables. Same thing for leg 2. To 1, dot, 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 to 4. And this operator acts on the super amplitude that at endpoints. And of course, as you say, the other ends are set to 0 in here. So the super amplitude needs to obey, and this is a natural point then to stop for a second, but we want to impose that the super amplitude is, is supersymmetric in the sense that by acting with the charges which we have defined, here I have to be careful about high-low indices, because and we want this to be equal to 0. So the next question in this linear flow of logic would be, okay, what quantities can I write at lower points that have these properties of obeying to that relation? Yes?
This amplitude is low, so all
Mm-hmm.
the legs are plus.
Yes, and the reason that all the legs are plus, I mean, this is of course an example of MHV amplitude, and then they are not associated, they are associated just to the 1 as the differential operator. So here I have like 4 Grassmann variables for leg 1, 4 Grassmann variables for leg 2, nothing for the other legs, and this is a component amplitude. You want to do, I mean, a question I got a lot in the breaks is how about fermions, right? Or how about scalars? If we find a smart way of packaging a super amplitude, then you start being able to generate almost automatically, or automatically, without almost automatically, I mean, by acting with differential operators of the form, you start being able to generate amplitude involving scalars, involving fermions, which will be the one of a corresponding supersymmetric theory. And of course, these are simple interactions involving other fields, not just gluons. And if you want to consider a non-supersymmetric theory, you could have, in principle, more complicated interactions. But this is a very easy way of moving through the multiplet. Okay.
So why are you acting with all 4 of them? So you're only interested in the A part, you're only interested in the fermion part, so that's why you're acting with
This is an example, so I'm interested in everything.
Yes, but
Yeah.
since you're acting with all 4 of the differentials, you're only extracting the part of the superfield that is A minus.
Yes, indeed. So this would be a minus, and then all the rest is plus, which here is just identities.
And therefore, by the minus, you mean that your legs are all like A fields, not the lambda fields.
Yes, indeed. And do you want to have a lambda field? Perhaps you just take away one of these, and then it will be an amplitude, and then you need another fermion, right? So leg number 3 becomes a fermion. So you move around in this particular case, and you are able to move through the multiplet. Okay, very good. Anything else here? The way I'm using this formalism is already elementary here, and but however, there has been a jump in what you see on the blackboard right now, so make sure you are okay with that, even from the point of view of notation. Part of the story, which I'm trying to tell, is also the fact that, well, one of the selling points of spinorilicity is also the fact that you get a very simple expressions for supercharging out of that. So this is an hybrid of the usual superspace Grassmann variable approach to supersymmetry, and also spinorilicity, right? Because here we are using the fundamental spinners in that. Okay, so I have 5 minutes left, and I think I am gonna just claim something, which I will then develop and hopefully prove in the afternoon. So I would like to focus on lower points. And claim that this object, which I call suggestively a delta function of Q, and I define more explicitly as the product of Q with my Q as low indices, very good, like this. And I can write even more explicitly, this is the form in which I use it, as the product of this particular combination of the summation for I different from J of Ij, angle brackets, eta Ia, eta J, A. Is solves. So this is the simplest thing, at least as far as I know, that can be built that has the property of solving these conditions. And this is very suggestively written in the form of a delta function of Q. To this, remember that if you want to write a delta function for a Grassmann variable, this is just the Grassmann variable itself, right? Here, we have up to normalization. We have many of them, and if you write down this explicitly, is the combination of all possibilities, both in terms of our symmetry indices and also the spinor indices 1 and 2. And again, there is a symmetry factor linked to the fact that each of these contractions has 2 terms, really. And then this is writing the Qs explicitly. Is it obvious that it obeys those relations? It's not obvious to me. So I think that the topic for the beginning, at least for the afternoon, will be actually showing that that obeys the properties. I think there is time, however, for a couple of questions, since I am 1 minute ahead of time. Okay. Then I'll see you in the afternoon.